Assalamualaikum warahmatullahi wabarakatuh and a very good day. So for today's presentation, I would like to share on my research with title Materials Properties of Lightweight Spiral Hybrid CMT Epoxy Composites Enhanced Reflection Loss. So I am Fadzidah Mohd Idris from University Science Islam Malaysia. So for today's presentation, I would like to present on the introduction, materials and methods, results and discussion, conclusion, and finally references. So for the introduction, during pandemic COVID-19 previously, there is actually an increment in the usage of various electronic devices. So therefore, almost all people around the world now live within range of a mobile cellular network signal, with 90% living within range of a 3G quality or higher network, for example 4G and 5G. So this accelerating growth of higher frequency device creates more electromagnetic interference pollution that cause disturbances on the equipment and systems, especially for medical, industrial, commercial, and military applications. Therefore, electromagnetic interference radiation, or it is well known as EMI radiation, is actually a wake-up call for everyone because continuously exposed to electromagnetic radiation for a considerable period of time is also potentially harmful to our biological systems. And in Sustainable Development Goals 3, which to ensure healthy lives and promote well-being for all at all ages, it is important in reducing the environmental risks from the harmful electromagnetic interference. Thus, many research interests focus on producing more electromagnetic absorbing materials that are effective in attenuating these unwanted electromagnetic energies. Therefore, our primary goals for this research is that we want to produce or we want to synthesize materials that can effectively absorb the electromagnetic interference radiation, which is harmful to our biological systems. Therefore, in this research, we successfully synthesized multi-wall carbon nanotubes with the structure of spiral and twisted fiber. So this spiral and twisted fiber is actually important in order to have multiple reflections in the fiber that can enhance the transmission route and absorb the electromagnetic interference pollution. So for this figure, we can look at this figure. So this is the incident wave, and then this is our absorptive layer or our materials, and there is metal backing here. So there is actually multiple reflection in the sample itself. So it could reduce the reflection and it could reduce the interference pollution. So one of the example of our application is that we can try to use our materials and coat on the surface of armored vehicle. So this in front of the armored vehicle is our coating of our materials. So the other example is that, for example, this is flexible honeycomb structure, and then this is the electromagnetic radiation, and there is electromagnetic absorption and electromagnetic reflection as well. But the electromagnetic reflection is actually minimum in this case. So other than that, application is that we can use it for phone pouch and then cap and then casing, vest, apron, and watch. For methodology, we have divided this research into 3 stages. So the first stages is we are using cobalt ferrite and iron oxide, and then we try to crush it into nanometer size region by using high energy ball milling, and then we are using furnace for sintering process to have the full phase of cobalt ferrite and Fe3O4 or magnetite. So for the second stages, this is for the preparation or synthesis of carbon nanotubes. So we are using our setup, which is thermal vapor deposition tube, and then we have argon gas as the gas carrier, and then we have ethanol as the carbon source, and we set it at certain temperature, which is 700 degrees Celsius for 30 minutes for the reaction time. And finally, the output is we have successfully synthesized carbon nanotubes. So next step is that we try to mix carbon nanotubes with 8 weight percent in epoxy resin. So the carbon nanotubes is used as filler, and the epoxy resin is used as the matrix. So we are using only 8 weight percent because by our review, If more than 8 weight%, for example 10 weight% loading of multi-wall carbon nanotube, it is actually did not differ significantly from the composite sample with loading of 8 weight%. In fact, if you are using 10 weight%, it is hardly to disperse well the multi-wall carbon nanotubes, the fiber, in the epoxy resin. So we try to disperse the multi-wall carbon nanotubes into the epoxy resin by using high speed mixer at 3000 rpm. And for the last stages, which is the third stages, so after we have mixed the multi-wall carbon nanotubes with the epoxy resin, and after we have well mixed it, so we pour it into our manufactured sample holder with certain dimension according to which frequency that we want to measure. For example, X band frequency range from 8 to 12 GHz and KU band frequency range, which is from 12 to 18 GHz. And then we measure the microwave characterization of the sample by using vector network analyzer. So this is the important equipment in order for us to know the reflection loss of the materials. Other than that, we are using TEM for the particle size, and then we have used FESAM or field emission scanning lateral microscope to know the micrograph of the sample, Raman spectroscopy to have or to observe the defect and gravitization in the sample. So these are the details on the materials measurement and characterization. So we are using 5 different measurements for our sample, which is X-ray diffraction for phase analysis, transmission lateral microscope for particle size analysis, field emission scanning lateral microscope for surface morphology, and Raman for structural analysis, and the last one is vector network analyzer. This is for the microwave characterization analysis. So next is our results and discussion. So for the first one is by using X-ray diffractometer. This one is to identify the phase analysis. So these are the X-ray diffraction pattern of composite samples, and all of these samples synthesized carbon nanotubes mixed with epoxy resin. So E is the epoxy resin. So we have labeled it as SF, SC, S1, S2, and S3. So S1, S2, and S3 is actually by having mixture of different iron oxide and cobalt ferrite percentage as the catalyst to grow carbon nanotubes. For example, S1 is actually 20% of iron oxide mixed with 80% of cobalt ferrite, and then we use it, the mixture, we use it as a catalyst to grow carbon nanotubes. So for S2 is 50% iron oxide mixed with 50% cobalt ferrite and use it as catalyst to grow carbon nanotubes. And the S3 is 80% of the iron oxide mixed with 20% of cobalt ferrite used as catalyst to grow carbon nanotubes. So we could see that actually carbon graphite or hexagonal gravitic phase of carbon reflections arising from parallel nanotube stacking layers and basal hexagonal carbon atomic networks. And CNT diffraction peak intensity depend on the morphological orientation of CNTs. So the X-ray beam creates 002 peaks when it hits a single wall of CNT. So actually this is the 002 peak, which is dominant for carbon peak, carbon graphite peak. So the additional hexagonal peaks arrays are generated by an empty central core of CNT following the passage of X-ray beams. And the CNT strings having that different size and shapes with curved graphene layers, most of the carbon's peak was suppressed and could not be observed, leading to peak shifting and broadening. So we could see that this is actually broadened in the FWHM or full width half maximum. So it is broadened actually for the main or dominant peak of carbon graphite. And other than that is actually suppressed. And the next higher peak is comes from the iron carbide. So the presence of iron and carbon during the CFD process results in the formation of iron carbide Fe3C phase. So this is actually the Fe3C phase. So this is the TEM result for various samples. So the average diameter size of SF and SC are 133.6 nanometer and 36.2 nanometer respectively. On the other hand, the average diameter size of S1, S2, and S3 are 56.7 nanometer, 64 nanometer and 75.4 nanometer respectively. Next is for FESEM, or Field Emission Scanning Electron Microscope. So this is the FESEM micrograph of synthesized spiral carbon nanotubes with SF, SC, S1, S2, and S3. So the presence of bundles and entanglements that consist of 50 to a few hundreds individual CNTs is due to the strong van der Waals forces. So most common structure of synthesized CNTs are straight-like, spiral, twisted carbon, and spring pasta-like structures. So fibers prefer to assume a spiral coil formation and highly aggregated, and then having carbon coil-like structures actually can lead to a wide range of uses, such as an electromagnetic wave absorbing materials, whereby it helps in extending the route for the EM wave signal being transmitted in the sample. And the consistent insertions of pentagon-heptagon pairs of at junctions is one of the reasons for the creation of coil or fiber-like structure. So size and shape affect the performance of EM wave absorber. Smaller particle size will result in higher surface to volume ratio attributed to better and unique materials. Next is for Raman spectroscopy. So for this measurement, it is specifically to identify the D band and G band. D band is the defect and G band is the gravitization. So there are two main peaks can be observed, which is disordered carbon or structural defects at 1350 cm-1 correspond to the D band. So this is the D band. And then there is another peak, which is G band, which can be observed at wave number 1570 cm-1. So G band indicates the movement of two nearby carbon atoms in the opposite direction. Meanwhile, the staging disorder defects at the tube end and curved graphene layers attributed to the D band. So low gravitization of nanocoils is indicated by a large D band peak and a broad G band peak. So we could see that this is the defect band or D band. So it is large compared to gravitization. And then we can look at the half of the maximum peak. So it is broad bandwidth here. So low gravitization of nanocoils is indicated by a large D band peak and a broad G band peak. The intensity ratios ID over ID for the D and G bands are consistent at around 1 for all samples as shown in this figure, and it indicating either a defective structure or a low degree of gravitization in the carbon nanotubes. So the ratio of ID over IG values of CNT showed a defective structure or a lower gravitization degree. So in general, EM wave absorption benefits from low conductivity and proper dielectric loss. In other words, the presence of defects in the structure is due to the presence of hollow structure, the spiral structure in the sample. So next is for vector network analyzer, which is used to measure the microwave characterization of the sample, which is the most important characterization in order to obtain whether our sample is higher reflective or absorbing. So minimum reflection loss peak at certain frequency refers to an electromagnetic wave being absorbed by the materials. So these are the three examples of materials being used to measure the microwave characterization. So this is 1 mm, 2 mm, and 3 mm. So the minimum reflection loss peak for a thickness of 1 mm here, okay, could not be observed for all samples reflecting the formation of resonant peak is actually at higher frequency range. And the reflection loss peaks for each sample resonate at much lower frequency range as the thickness rises from 1 mm, 2 mm, and 3 mm. So as the thickness increase, the frequency range is reducing. So next is it is because of the transition aligns with the geometrical effect matching requirement. So as for S1E and S2E, it can be observed that the RL peaks of thickness 3 mm, this one, are negative 23 dB at 12 GHz and negative 21 dB at 14 GHz respectively. So however, for sample S3E, we could observe for thickness 2 mm and 3 mm at different frequency with different reflection loss. So actually, in the whole sample, when we try to mix with epoxy resin as the matrix, So epoxy composites actually play a critical role in the absorption of EM wave by absorbing the EM wave energy and mitigate the radiation. This event occurs via the interaction between interior electrons and exterior EM wave radiation and inner electrons of the epoxy composites. So actually by having value of reflection loss less than negative 10 dB, so it shows that the sample is highly or effectively absorb the EM wave signal. Finally, for conclusion, smaller particle size of catalyst results in higher surface to volume ratio. The carbon structure forms, which is spiral, twisted, straight like hollow fiber, assists in absorbing the incident electromagnetic wave by having multiple reflection in the composite samples. The ratio of Ig over Ig indicates defective structure, contribute to stronger electromagnetic wave absorption. As the thickness increases, the reflection loss peak shift to a lower frequency range due to shift of matching frequency. And at thickness 3 mm for S1E, S2E, and S3E, showing the value of RL is less than negative 10 dB, that indicates 90% of the EM wave was absorbed. The RL peaks with the minimum values was obtained by S1E and with negative 23 dB, and for thickness 3 mm and with broad bandwidth of 6 GHz. So a greater EM wave at a lower field fraction depicts a promising EM wave absorbing at a wide range with light mass, strong absorption, and it may have potential application to be used as an electromagnetic absorbance. For the acknowledgement, we would like to acknowledge Ministry of Higher Education for financial support and the Fundamental Research Grant Scheme with this research code number. That's all from me. Thank you.